Hello and welcome back. Today's recorded session will be Chapter 13 about the spinal cord and spinal nerves. We begin here because as we take neurons and neuron chains that we call nerves and we start stacking them up, the simplest place to begin is the spinal cord. So Chapter 13 you can see below, where we will consider specifically the pathway of sensory receptors sending messages to the spinal cord. And we will consider a particular kind of processing and reaction called reflexes. The processing will send out a command to effectors, shown on the right. Effectors are only of three types. So our nervous system can only control our muscle fibers, our adipose tissue, and the glands that secrete are of various substances. Chapter 14 will be about the brain, and we will be moving up a step of complexity. That step of complexity is because of the massive number of neurons and the different regions, and actually the specialization of different regions that have led to the brain functions and the characteristics of humans that we see. So let's begin with Chapter 13. Its anatomy gives a clue to its understanding, its organization. The spinal cord is the central nervous system organ that connects to the periphery, and it is regulated by the presence of those vertebrae. You can see in this figure how spinal nerves are arranged to depart from the spinal cord cavity out into the periphery at the junction of each of the vertebrae. We number the spinal nerves beginning with C1, cervical region 1, which represents the gap above the C1 vertebra. So that means we descend C1 through C7 above the vertebra. Now, at that point, we actually number C8. Although there are only 7 cervical vertebrae, there are 8 pairs of cervical nerves. C8 is below the C7 vertebra. From there on, we number the pairs of spinal nerves based on what vertebra is above it. So T1 through T12, L1 through L5, and then surprisingly, in that single bone, the sacrum, we see the departure of 1, 2, 3, 4, 5 sacral nerve pairs. Even though this is a fused bone, the pattern of a pair of nerves between each pair of vertebra is retained. Now, we do notice that it's a compacted and covered spinal cord down to about L1. And there the wrapping disappears, and you see a bundle of separate nerves in the spinal cavity. That means this name, the cauda equina, which stands for horse's tail, because it resembles that different hanging fibers or hairs of a horse's tail. You can see on the right that the cross-section of the spinal cord varies quite a bit depending on the number of nerves and nerve connections that are serving that region. Each cross-section shows a region of central gray matter, and the gray matter are neurons that have no myelin sheaths on their axons. Gray matter essentially is a region where neurons have naked membranes, and therefore anywhere on the body of the neuron, anywhere along the neuron, a synapse can form. So these are processing areas. This is where a message comes in and is processed and a response goes out. Surrounding the gray matter is the white matter, which is myelinated or basically signaling or transmission neurons, and we see this white matter, gray matter division in every part of the spinal cord. Of course, where regions have more nerves connecting in, such as that region right in the pectoral region where all of the nerves that serve the arm and hands are located, And in the pelvic region, where all the nerves of the legs and feet connect, there are bulges and larger diameter regions which serve a relatively small number of effectors and sensors. Will show a diminished size like we see down below. So looking at these individual divisions, the C3, we can see a typical anatomy. It is bilaterally symmetrical around the midline. There is a large separation of lobes in the anterior side labeled the median fissure, and three small folds, the median sulcus and the lateral sulcus at the posterior side. The two connections to the lateral aspect of the spinal cord are labeled the dorsal root and the ventral root, and they do have a noticeable ganglion. That's an area where gray matter exists outside the spinal cord. And those nerve connections come together into a spinal nerve and the extreme lateral aspect. The central canal is shown in the center of the gray matter. Notice from all the other regions, that's a consistent feature of the spinal cord. A gray matter, kind of butterfly shape, it always looked like to me, with a hole in the center, the central canal. So gray matter, white matter, and connection and division, the spinal nerve dividing into a dorsal root and a ventral root. There is a functional correlate to this anatomy. Sensory messages arrive in the spinal cord through the dorsal root. So input into the spinal cord comes from the dorsal side. The processing occurs in the gray matter, and certainly a significant amount of that is sent up through the spinal cord to the brain. But there is also reflex processing that goes on, and effector messages would go back out through the anterior horn of that gray matter, and it would go through the ventral root out to the effector. Now I want to emphasize that point by using the pointer, and hold on just a moment. Well, I turn the pointer out. So here we have the spinal nerve and a division. Sensory messages come in here. There's some processing here in the ganglion, and it enters the spinal cord here through the posterior gray horn. Processing can occur here, and if a message is sent out, it goes from this anterior horn to the ventral root, and the message then goes out to the body. The spinal cord is shown in one of these wonderful staged dissections to reveal the different layers. The outer bone covering that protects it, that basically makes it impervious to body shocks, but the junctions between those vertebrae allow lateral openings so that the spinal nerves can enter and connect to the spinal cord. I want you to start at the top with the gray matter butterfly extended up here above the white matter, and it shows that these roots, the ganglia to the, in this case, the dorsal root, these are the sensory messages. Notice how they spread out and connect to that posterior gray horn all up and down that posterior surface. On the other side, the messages from the anterior horn are likewise spread out through this whole region. So even though it enters at one place, you expect them to fan out and basically provide connections all through this region of the white matter, gray matter of the spinal cord. Now right here are the meninges. The meninges are specific coverings of the spinal cord and brain. They not only separate the central nervous system physically from the surrounding tissue that is serviced by the blood plasma, but they separate it chemically as well. That means this interior part of the central nervous system is regulated on a very different basis. Blood does deliver nutrients throughout, but those nutrients are and oxygen are regulated in their passage into the central nervous system by the astrocytes and oligodendrocytes that the neuroglia that we saw. The capillaries are covered by astrocytes, and so the brain regulates and the spinal cord regulates its own chemistry. It has a different fluid called cerebrospinal fluid. So you can think of these meninges as a physical and chemical barrier separating the cerebrospinal fluid portion of the central nervous system from this surrounding portion, which is serviced by blood plasma. Now, the meninges consist of 3 layers. The so-called dura mater is very, very tough, flexible. It's sort of like that flexible plastic wrap that's on the packaging in Walmart. Very hard and very strong. The pia mater is shown here, and it is a lighter and a more delicate tissue, but it binds specifically to the outer surface of the white matter itself. We're going to see that same adhesion in the brain. Between, there is a space that is basically maintained by little rods that keep the dura mater and pia mater separate, and this is called the arachnoid mater. The arachnoid mater is actually, like I say, a flow space for cerebrospinal fluid to circulate. And because it looked kind of thin and like a spider web, arachnoid refers to that. So this is the separation. Cross-section shows, here we go, the spinal nerve splitting into posterior and anterior roots and entering the spinal cord. The posterior root is delivering sensory messages. The anterior root is sending out motor messages. It is important to maintain this spinal cord physically because nervous tissue depends on synapses. That's a space. It's much more difficult to maintain a space than it is just to lock something together. So that's why we have a delicacy to nervous tissue. That's why when we fall down, our arm might get a bruise, but our head would get a concussion. When we look at the cross-section, we can clearly see that this pia mater is attached to 2 ligaments called denticulate ligaments that basically suspend it and maintain it in this space. It is surrounded by cerebrospinal fluid, which provides a hydraulic cushioning. When you hit the ground, these ligaments come tight and they keep your spinal cord from slamming too hard into the surrounding material. Notice the arachnoid mater and the dura mater surround the entire central nervous system and spinal cord. But that's not all. Look at this. Outside the dura mater, you see fat globules. That adipose tissue is there not for energy storage, but for packing. A soft and flexible material that again cushions the spinal cord as it's held within its protected spinal cavity. Here's a real dissection, and it is hard to see all aspects of this. This is that anterior fissure. You can actually see it with the pia mater drawn back. This pia mater, as I said, is more delicate. See how it surrounds everything? And you can see a spinal nerve out here has branched to the anterior root, and you can only see the anterior root. The posterior root is around to the other side. So this is the area. Notice how it fans out in its connections all up and down the spinal cord. And basically this is where the motor commands are going out. You can see the dura mater, which has been flexed back. It is the tough covering, and this right here is a denticulate ligament See how the ligament essentially encases and holds this in place. Now this has been, as I said, dissected and spread apart, but ordinarily these ligamentous fibers would circle the entire spinal cord, suspending it in its fluid space. When you have, and there's good news to bad news to the meninges, the disease of an infected meningeal cavity is called meningitis. It's very, very difficult because of the meninges to get a pathogen or toxin into the spinal cord. The body protects the brain and spinal cord utmost. However, once you get it in there, it's difficult to treat it. And so a spinal tap is done. This posture will cause the vertebra to open like this, and the doctor is probing through that opening, trying to put a needle through the dura mater and into the arachnoid mater. When that is punctured, the pressure of the spinal column can be measured and spinal fluid can be withdrawn. The pathologist would then determine whether there is any infection or toxin that needs to be dealt with. When we look at the organization of the spinal cord, we do see a rough organization. Now, not good enough. There are not dividing lines or fences between these regions, but the functions are partitioned into somatic, voluntary, and skeletal muscle all sort of fit together in your head, and visceral and autonomic, and the organs of your body which are regulated subconsciously all fit together. So let's take a look here. We will label the overall regions of the spinal cord, this gray matter, as the posterior gray horn, the so-called lateral gray horn, and the anterior gray horn. And those are related to the connections of sensory input grading to motor output. Over on the other side, these colored regions show you that the somatic signals from your voluntary system, and mostly your skeletal muscles and sensors, come here. The visceral signals from your organs are processed in the gray matter here. And then for motor output, the signals going to your organs come from this lateral gray horn, and the signals going to your muscles, look at that big region because there are so many muscles. The somatic motor impulses go out from this anterior gray horn. Now, because the way we draw figures, we kind of want to talk about this on different levels. Of course, each of these diagrams overlap and basically apply to both sides. So in addition to having this pair of nerves at the particular junction that serves a specific level of the body up and down the spine, all of these functions are partitioned left and right. The actual dissection, the actual section shown down here below, shows you gray matter and white matter, the posterior sulcus and the anterior fissure. It shows you gray matter and white matter division into the posterior horn and the anterior horn, and basically the progression of somatic sensory is not well defined by any natural feature from the visceral sensory. And as we move anteriorly, visceral motor and somatic motor regions for nerve processing. When we cut across the nerve, lo and behold, we have a reminder of the naming that we did in muscles. Do you remember how there was a muscle, and then there was a fascicle, and then there was a fiber? The muscle was covered with an epimysium, then it went to a perimysium, then it went to an endomysium. In nerves, we're going to use the same naming system and replace myo with neuro. So here we have a spinal nerve shown in its entirety, covered by an epineurium. When we look inside, we see bundles called fascicles. Here's a fascicle. That fascicle is covered by a perineurium, and this bundle is full of myelinated axons and individual nerves. These are covered by an endoneurium. When you look at the actual tissue over here, you see different levels. Here's a big blood vessel, which is between the fascicles. That's providing flow into the larger spinal nerve. But here's a blood vessel that's within the fascicle and basically nourishing the individual nerves and their axons surrounded by endoneurium. So we're seeing here a repeat of something the body does well. The body makes tubes very well. We saw tube structure in muscles. Now we see tube structure in nerves. We're going to see on a different level in organs. The blood vessels, the lymph vessels are essentially tubes. But basically, when we look at the spinal nerves connected right at the spinal cord, we see that there's a tube within a tube within a tube organization, which is a reminder of what we dealt with in muscles. When we look at the peripheral distribution of nerve impulses on spinal nerves, now this is just showing the left side of the spine and a cross-section of a representative region, and I believe this is blown up here. There's a spatial relationship for the input of sensory information. So red is showing input from somatic systems, mostly muscles, and as you would expect, those that are coming from nerves from the posterior side, curving around at that near 90-degree angle into the dorsal root ganglion, those are from exteroceptors on the back. They grade into the exteroceptors, the sensors in the body wall and limbs. From the lateral aspect, those are shown right here. So these are the somatic pathways. Now, what about that little dot? That little dot shows the presence of gray matter so that these signals can actually be received and then hooked up to different pathways for distribution. So where we see this bulge in the external nerve, we're going to call that a ganglion, and we're going to realize that that represents a spot of gray matter outside the spinal cord. Now, the interoceptors, which are sending messages from organs, somatic messages, are coming again spatially from the back, from the body wall and limbs of the side, and this particular ventral pathway going through this ganglion is coming from the visceral organs. So in addition to the sensations from outside the body, we're constantly monitoring things like pH, chemoreceptors, temperature, other conditions of blood quality in those organs. And here come those sensory messages. Now, after the ganglion, those come in and are distributed to the somatic center and to the autonomic center for reception of sensory messages. Now, this is happening, in this case, from the right side. This pattern of wiring would be repeated on the left side. Now, the distribution and the wiring for motor commands, once you go in, there's going to be processing that's possible. It can occur upward in the brain, but it also can occur, if it's a reflex, right here in the spinal cord. And a motor command is generated. We're going to talk about that later. So from this region, The visceral motor commands are going to be going out through the anterior root and down through these sympathetic nerves to the organs that basically are going to be producing the regulation through muscle, gland, and fat signals that represent the central nervous system's command of our basic metabolism. The somatic signals are sent from this anterior gray horn out through the anterior root, where they are split up. You will notice that these basically go spatially to the back or to the side and front. There is one difference here, though, and that is from the visceral motor nuclei sending a message to this sympathetic ganglion. Notice that bulge. Again, this is where synapses occur for the distribution in a different way to different nerves, and these interoceptors are shown in black. Now, because a particular motor command may affect more than a single organ, you may in fact wish to activate many systems at once. These then can lead out to any area of the body that would be an effector response. Because of this segmental organization that's related to the vertebra, that means that the nerve sensitivity produces adjacent regions on the outer skin. So you see these regions called skin regions or dermatomes diagrammed here. Notice this is on the left side, we are seeing the anterior side of the body. On this side, we've turned it around. So first we see that these regions of sensitivity are basically related to the spinal nerve and its location, and it produces a band of sensitivity. There's the T3, which you can see ducks under the armpit and emerges here, coming straight across to the sternum. In general, these do descend. Here's T9 coming down to here and then descending more as it comes over here to the midline. These are related to regions of gravity-affected regions, and in some cases they produce these swirls of sensitivity. You notice that because the connections stop basically right here, the legs and the arms contain a kind of an interesting mosaic of these regions. One place you can see this naturally is when you have a case of shingles. Shingles is an irritation of the skin that is caused, and of underlying tissue, that is caused by the activation of the chickenpox virus. When you get over chickenpox, you retain some virus, and notably you retain it at the junction where the spinal nerve enters the spine. Now that means if the chickenpox virus in later life flares up, it irritates that nerve, and especially the motor nerve, and it sends out messages of inflammation. Inflammation causes reddening, greater blood pressure, opening of the blood vessels, so there's swelling, there's often itching, and there can be pain. But you can see the pattern of the dermatome. This may be one, it may be two. It's a little bit wide here for one spinal nerve. But because this happened on the left side, and because that arcs downward, this pattern of irritation is seen as a rash with a particular dermatome shape. Notice that it does not cross the midline. The other side is apparently not being activated. But shingles can produce symptoms ranging anywhere from just small bumps, which may not produce any particular sensation, but just something that's visual, all the way up to kind of massive swellings, itching, and pain that requires medication, a reflection of the spinal nerve organization. When we look at the actual connection of nerves, We will see departures of nerves for the arms and legs, which produce particular swellings of the diameter here in the lumbar and sacral plexus for the legs, and up here in the so-called brachial plexus for the arms, shoulder, hand, and wrist. These particular nerves are named in a very logical way, and this is where you're going to get payback from the language of anatomy. You remember we asked you to learn the axial region. We asked you to learn the radius and ulna, and here is a new nerve, since there were three. The median nerve is named for position. Here is the sciatic nerve, one which, because of its lower back positioning, produces quite a bit of difficulty in nerve pain for many people. I'm not going to cover these plexus organizations in detail, but I wanted to show you one example of a partial anatomy of the cervical region, because it speaks to some things that are universal and also foreshadows some things we'll be talking about later. Up here in the cervical plexus, you can see the base of the skull has been represented well, and you can see the cervical nerves that, as you can see, are providing sensation, inputting through these spinal nerves, and also motor command, connecting to things like muscles. So if they connect to muscles, if they're controlling muscles, these are motor rootlets. If they are bringing sensation in from surrounding regions, for example, we have sensation in the entire face, head, and neck region, they would be brought in through sensory nerves. We also see the numbering we talked about, C1, right at the base of the skull, and followed by 2, 3, 4, and 5 in order, following the naming system we just talked about. Here are nerves that are serving the hypoglossal, below the tongue region, and nerves that serve the face and serve internal and external connections to the base of the brain. Now up here we see a couple of nerves that are labeled cranial nerves. The spinal nerve pattern is repeated when you come up inside the skull, and there are 12 pairs of nerves that essentially attached to the brainstem. These are called cranial nerves. And the two that are shown here are called the accessory nerve, 11, and the hypoglossal nerve, 12, which are cranial nerves. Although they are inside the skull, they are attached directly to the brain stem and the base right below the cerebrum and in front of the cerebellum. They are considered peripheral nerves. You can see how the neck is richly supplied. Here is where those transverse foramen are important. We're going to see later those blood vessel called the vertebral artery go right through them up into the skull. So when we look at the brachial plexus, we see a couple of interesting things. The characteristic of the neuron was branching and multiple connections. And the wiring diagrams that we do with electricity, like a car or a house, are all simple, because if you don't force the electricity through a single path, the appliance won't work. Whereas it's a little bit different with these electrochemical cells. The characteristic of each cell is to be connected by synapses to hundreds of other cells. In the brain, we're going to see that go to thousands, tens of thousands, and in the cerebellum, even a place where those anaxonic neurons connect to an estimated 200,000 other neurons. So the flow, the division of these electrochemical impulses that produce the EEG waves that we measure, electroencephalogram signals, are characterized by spreading those impulses out for processing in a large number of areas. So we see that here, and the basic naming. Now don't memorize this, but here's what I want you to notice. Here is the spinal nerve C8, which immediately seems to merge with, I'm sorry, that's C6, merge with C5. So they come together here, but right down here, they split again. So this region is called the spinal nerve. These are called roots. They give way to trunks, divisions, and cords, regions where you'll notice there's a splitting and then a rejoining. So it is very difficult to follow a single nerve out of this system when it could be going down this way, it could be going down this way, it actually down here could connect again over here. So mixture of these nerve tracks is very much seen at this whole nerve level. So the major nerves are basically named. Here's radial, ulnar, and median, depending on where it's going. Here are palmar and digital nerves, basically a branching tube system that's going to provide the input sensation from all areas of the body to some gray matter that will process response, nerve processing, and then motor commands that will come back out to every part of the body in order to control our behaviors and our responses. The lumbar and sacral plexus control a lot of tissue, but because these are the main load-bearing parts of the body, it's not that hard to control a big muscle. It really isn't. It is the dexterous parts or the complex parts of our body that require lots of nerves. So the dexterity of the hands require lots of nerve connections. The complexity of the eye and the ear. The tongue, which is used for speech and eating. Language comes out of the dexterity and the independent control we can exert on our tongue. So that's where you're going to find lots and lots of nerve connections. Here we have on the leg the major sciatic nerve giving way to the tibial and sural nerve, the common fibular nerve, superficial nerve are all named appropriately for region. You can also see this diagram with purple, yellow, and blue showing the connections of different nerves and how they adjoin each other on the superior, inferior, and posterior aspect of the foot. These regions are essentially border to border, providing basically no area of insensitivity. Now that we've kind of got an idea of the overall anatomy, the overall mapping of genes, we have to think about what's happening to these nerve impulses, because they certainly are sending a message, for instance, from a specific sensor for touch or heat, but they go up and are connected to other nerve networks by synapses and those branching ends. So we see that there are a number of different ways that nerves can be organized. Number one, divergence, where one neuron splits the signal up and transmits that to two receiving neurons. Convergence is different. We have sensors all over here, but we don't have to have an independent track for each one of them. They can converge on a central signaling line, typically white matter, which then would send the message all the way up here. Serial processing is straight line. We've kind of alluded to that before. Parallel processing is a very special kind of divergence. Notice that each neuron above, two of them, splits to connect to three below. This is something that is done where very fine-grained division of sensation is required. When you think of the world in front of you and how light carries information to your retina, the whole world, this 180-degree view, is going to be compressed on a retina that's basically that big. Each retinal cell is receiving a part of that image and is required to transmit faithfully the conditions of light intensity and color. So this is a place where a patch might be activated by a single retinal cell because it is small and we want the best visual acuity possible. A small area is activated by a single cell. This is a interesting one called reverberation. It relates to that thing in homeostasis called feedback, in this case positive feedback. Here comes the impulse. Maybe that impulse is a signal of nausea. So it passes down this pathway. But as it passes, an axon of the receiving cell curls back and stimulates the prior cell again. So this is how the sensation repeats and builds toward the conclusion. So nausea from alcohol poisoning leads eventually to vomiting. Pregnancy, Bracken-Hick contractions lead to faster contractions, or closer together contractions, and more intense until the baby is delivered. Positive feedback results from this kind of nerve connection. Reflexes are interesting, and they are a physical reaction by an effector that is processed not in the brain, but in gray matter outside the brain. So this is shown for a reflex to a painful stimulus, placing your hand on a tack. After that happens and you stimulate the pain receptor shown here, it is transmitted into the sensory receiving region for somatic sensations, conscious sensations. And in the posterior gray horn somatic region, it is transmitted to a processing area, and you notice a synapse forms. Now this white neuron is going to cross over. By the way, keep that in mind. We often will receive a sensation from one side and cross it over to the other side. This signal is going to the brain. That signal is the ouch. That's the pain you feel. But the reflex, you'll notice this divergence, is hooking to a motor neuron that's connected to, guess what, a muscle. Now it turns out it's the biceps brachii, my favorite muscle. So what happens when it goes directly to the biceps? We flex the elbow and remove the hand from the painful stimulus. Now the reason I like this example is that it's actually faster to jerk the hand back than it is to get the pain message all the way up to the brain. So if this were a tack or if this were a hot skillet, you might be reaching off to the side, not really looking at what you're doing. Your hand goes down on that painful stimulus and your hand jerks back. And you have time to actually go, what's going on? Ouch. So there's a time delay that you actually can perceive between the movement of your hand and the sensation of the painful stimulus. Of course, by the time you get the sensation under normal circumstances, the reflex has removed the cause. Reflexes are categorized in different ways. Are they genetically determined? You're born with them, like the jerk response from a hot skillet, or do you learn them? Are they something that's conditioned? There are certain things that we do that are on the border of somatic and autonomic. So for example, I very much had to learn how to balance my body. But right now, I've been doing it so long, I don't actually have to think about it, do I? I decide to stand up. The subroutine called balance measures the input from all my joint and skin and muscle signals and combines it with information from my balance organ about gravity, and I can maintain an upright posture. That's a long-term acquired reflex. Now, in terms of response, am I going to activate muscles, somatic response, or am I going to regulate an organ? Am I working on digestion or respiration? That's the difference between somatic and visceral. The complexity, is this one synapse and one line, or is it many synapses contributing to that reaction? The processing site is also important for reflexes. Are we processing it in the spinal cord, or are we processing it up in the brain? It turns out that that's not a complete list. At times, we have what's called a short reflex for local control of an organ system, where the controlling nerves and connections are actually within the system itself. That relies on other ganglia, and one that we'll talk about more second semester. So a stretch reflex, like the doctor. What are you doing when you hit that nerve? You can see it's that nerve right below the patella that hooks the tibial tuberosity so the quadriceps can extend the knee. But when you hit it, it basically jerks that muscle. There's a sensor right here built into this muscle spindle that sends a message, comes back out, and says basically extend the knee. That basic extension is a nerve test for the doctor, but what does it do for us? Let's say your foot comes down wrong, and the weight of your body is causing your knee to collapse. You weren't expecting that footing. Tightening the quadriceps muscle, in this case, doesn't extend the knee, but it arrests the flexion of the knee. It stops that bending. So you catch your weight as a result of this effector, this reflex, and you do not fall down. This is the muscle spindle, just showing you that the sensors are wound into the muscles, and they're spindle agents in order to sense the stretching, send the message to the spinal cord, receive the message quickly back from the efferent motor fiber that causes the neuromuscular junction to contract that muscle. Here is that particular drop the hot skillet. If you pick up a hot skillet, you not only receive a painful stimulus, but you actually have to do something to drop the skillet. This isn't just drawing your hand back. You're having to stimulate the flexors of the hand while you inhibit the extensors. So that's what allows you to open your hand and drop the skillet. This is a crossed reflex, a more complicated one, showing you the reflexes that relate to our overall body motions are sometimes requiring a number of connections. In this case, a painful stimulus as you step down. I don't know if you've ever had this experience when your foot comes down on something sharp or something hard, stepping on a gravel piece on a rock when you didn't expect it, and it produces a painful stimulus, and you'll often find yourself stomping down with the other foot and basically catching your balance while you withdraw. The other one happens very rapidly. The painful stimulus causes a complementary and opposite reaction in the extensors and flexors of the two legs. So what you want to do with your non-painful foot is inhibit the flexors of the knee and stimulate the extensors. So you want to straighten that other leg to catch your weight. At the same time, you're stimulating the flexors. I'm sorry, I said the knee, I meant the hip. You're stimulating the hip flexor to draw the hurting foot up. At the same time, you're inhibiting the extensors to allow for that motion. So you save yourself from pain, but also from injury. This is a developmental reflex. You'll notice the normal reaction in adults on the left when you draw a blunt instrument across their foot is to curl the foot around the instrument to basically flex the toes downward. That is because our primary job for the foot is to press down on the ground. And anything that affects the bottom of the foot causes that downward, that contraction of muscles to press down with the foot. This is the normal reaction in an adult. We do not have that reaction in an infant. There is sensation, but when you draw that across the infant's arch, basically the foot expands, basically flexes in all directions. Toes separate and basically flex backward away from the instrument. So this is something that we learn as we develop the ability to walk, run, stand. That also gives us what's called a Babinski reflex test. Do this on an adult, and if their foot basically flexes back from the stimulation, it's a sign of a nervous problem. So review this kind of central drawing. There is our white matter, gray matter spinal cord and the flared connections right here at the pointer. In this case, we are looking at the posterior connections. So these are sensory connections. They will be processed in gray matter and come out through these anterior or ventral motor commands and out to the body. Here is the pia mater, dura mater in the space between the arachnoid mater and the anchoring within the spinal cavity that allow the spine to be protected and covered by blocky bones. Remember, those bones are also supporting the entire weight of the body while they allow for movement and flexibility, but essentially the interior structural integrity of the spinal cord inside that flexible protective spine